and then start. All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First, please mute yourself during the talk, but if you have questions, you can unmute and ask your questions, or use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Dr. Meng-woo Guo, who is an assistant professor in applied mathematics at the University of Twente, the Netherlands. Prior to this appointment, he held postdoctoral positions at EPFL's Institute of Mathematics and the Odin Institute for Computational Engineering and Sciences at UT Austin. He received his bachelor's in engineering and PhD degrees in civil engineering, both with top honors from Tsinghua University in 2013 and 2017. His research interests spanned several areas in computational engineering sciences, of course, exciting areas, including model reduction, VVUQ, multi-fidelity data fusion, and probabilistic methods for scientific machine learning. Currently, he receives a financial support from Dutch National Instrument sector plan beta under the focus area mathematics of computational science. Today, Meng-woo will present an exciting topic, which is probabilistic methods for data-driven reduced order modeling. I'm sure we will hear an exciting talk today, but before I pass the baton to Meng-woo, let me ask a couple of questions to him just to get to know him better and make this seminar somewhat informal. Okay, first question, here you go. In your bio, you have listed several research interests like model reduction, UQ, multi-fidelity data fusion, and probabilistic methods for scientific machine learning, etc.
Yeah.
I know they are all related, but if you have to choose one that is the most exciting to you right now, what is it and why?
If I have to choose, I don't prefer, but if I have to choose, I would choose UQ. I think especially in the current era of scientific machine learning, UQ is a cross-section, right? Across scientific computing, computational statistics, machine learning, physics-based simulation, and DDPS, right? So I think the crossroad is UQ, and I'm the most excited about it. I'm also teaching UQ to the master students, and they are also quite interested in UQ topics. Yeah.
Awesome, awesome. I guess you are going to Siam UQ conference next year.
Yeah, indeed. It's in
Awesome.
Italy, a very nice city. Yeah.
I will see you there then.
See you
Well,
there.
second question, here you go.
Yeah.
How is it like being a professor at the University of Twente, the Netherlands? If I give you a minute to advertise your university here to audiences, how would you brag about your school?
Yeah, this is a very international university. It's inside the Netherlands. It's in the mid of Europe, but all of our teaching, no matter bachelor level or master level, everything is in English. So we have a variety of students from all the countries you can think of, and the diversity and inclusion is perfect here. So I welcome a lot of students from US and from China, from all the countries to our university to have bachelor or master studies or PhDs. And this is definitely one of the best environments you can get in Europe for international studies and research.
Awesome. Yeah. Sounds wonderful. All right. The stage is yours, Meng-woo.
Thank you. Thank you. Thank you for the invitation, the nice questions and introduction. And I value this very good opportunity to share some of our research results on probabilistic method for data-driven reduced order modeling, some established results and some more recent results. I often like to start my motivation by talking a little bit about digital twin technologies. Digital twinning is currently a very trendy topic in the computational engineering community. And when we talk about a digital twin, we are actually referring to a digital replica that persistently represents a unique physical asset throughout its life cycle, powered by big data and enabled by a dynamical synchronization between the physical and the digital twins. And in my personal opinion, the success of digital twinning would highly rely on the synergistic integration of physics-based modeling and machine learning together with real-world observational data. And this is actually perfectly aligned with the spirit of scientific machine learning. And in order to realize the dynamical real-time synchronization between the physical and digital twins, it is crucial to enable a multi-query real-time simulations. As I guess most of you already know, in scientific computing, multi-query real-time simulations are often described by a nonlinear, time-dependent, possibly also parametric partial differential equations. If we use full-order solvers with detailed code to solve these multi-query real-time problems, it may result to prohibitive computational cost. And this is why and where a reduced order modeling comes into the stage, right? So generally speaking, model reduction or reduced order modeling attempts to intelligently reduce the system complexity by representing high-dimensional physical systems in low-dimensional latent spaces. Just in case some of the audience may not be perfectly familiar with model reduction, just a few words about the general spirit of reduced order modeling. I'm summarizing the typical framework for model reduction into 3 R's: reduce, represent, and recover. So typically in the first step, we reduce a high-dimensional solution manifold into a low-dimensional latent space. And inside such a latent space, we represent our physical system in a low dimensionality, forming our reduced order system and solve along with it. Once we have solved the reduced states, and in the last step, we can recover or decode back to the full order size, right? This is a 3-step methodology: reduce, represent, and recover. In my personal opinion, the most tricky part is often the second step, the representation of the system inside the low dimensionality in our latent space. A classical treatment for this representation is through Galerkin or Petrov-Galerkin projection. We just project the full order systems into the reduced latent space, right? And this classical and conventional treatment through projection, or we call it projection-based model reduction, is often intrusive, meaning that we have to get the access to the inside of the full order code to extract the matrices or vectors or whatever elements we may need to formulate our reduced order system. And the numerical projection will also be problem dependent, and this intrusive nature will most possibly result in limited industrial relevance, which is not something we want. And this has been my and also many other colleagues' motivation to develop data-driven reduced order models in a non-intrusive manner. The holy grail in this area is to learn physically consistent representations of reduced order dynamics primarily from data instead of numerical projection to formulate the reduced order systems. So here I'm quoting Albert Einstein. As far as the laws of mathematics refer to reality, they are not certain, and as far as they are certain, they do not refer to reality. So basically, this has pointed out the importance of uncertainty quantification in scientific discovery and physical simulations. And of course, when we do data-driven model reduction in a non-intrusive manner, when we do the learning process, it is inevitable to encounter noise in the data as well as a variety of uncertainties throughout the modeling process. And this has been my motivation to use probabilistic machine learning to facilitate our data-driven reduced order models with a natural uncertainty quantification. And in the upcoming perhaps 40-ish minutes, I'm going to briefly review some of our research efforts in the last 5-6 years until very recent. There are 3 classes of methods I would like to discuss. Depending on how much physics we are incorporating into the models, we have the first method being black box method, basically using Gaussian process surrogate models to build reduced order models. And the second method is a gray box method. We try to represent reduced order dynamical systems with a probabilistic learning technique called deep kernel learning. And last but not least, we are going to discuss a third method, a glass box method using Bayesian inference to estimate reduced order operators. Okay, so my journey along this path started roughly 5-6 years ago in Switzerland, and we started with Gaussian process surrogate modeling. This method is no longer new. And maybe it's not that exactly exciting anymore, but it did set basis for a lot of follow-up considerations in the other method I'm going to introduce. So here I would still like to briefly discuss this method a little bit and also introduce our critical numerical tool, Gaussian process emulation, which will be also used in the other 2 methods in different ways. Okay, so we started with a very, very simple and straightforward idea. The reduced order modeling often seeks to find a low-rank approximation of the reduced order solutions. So the reduced order solutions will be space-time parameter dependent, and it is actually represented as a linear combination of a small number of reduced basis vectors over space with time parameter combination coefficients. Right, and in order to get the reduced basis vectors, we can use unsupervised learning, basically dimensionality reduction. And the most popular method, as you know, is linear PCA, or we call it proper orthogonal decomposition in the model reduction community. We just get the full order snapshot, solution data, and compress through linear PCA and get our reduced basis vectors. And then the question is about how to approximate the time parameter dependent combination coefficients. And here we are using a very simple tool. We are using regression to approximate the map from the time parameter inputs onto the projection coefficients onto the reduced basis, and use this regression model as a surrogate for our expression coefficients of the POD basis, right? So one step of unsupervised learning and another step of supervised learning. And after the training in the offline stage, the online stage is simulation free. We just need to evaluate the regression output plus a simple linear combination of the reduced basis, right? And in order to further improvement the offline training stage, we also tried multi-fidelity data fusion to reduce the number of high-fidelity evaluations to improve the efficiency of the offline stage. And also we tried domain decomposition for accelerations in large-scale problems. As I already mentioned, the regression tool we used was Gaussian process emulation or Gaussian process regression. Just in case you are not very familiar with this tool, generally speaking, in Gaussian process regression, we assume the prior on the regression function to be a Gaussian process with a given kernel function, perhaps also corrupted by an additive white noise. Conditioned on the training data of the input-output pairs, we can resort to a conditional Gaussian and have the posterior distribution also as a Gaussian process with a new mean function like this and a new covariance function. And in this case, for our regression function, in a predictive sense, we not only have a mean estimate, but also have the posterior variance providing us with certain some kind of uncertainty quantification as a confidence level. And in order to determine hyperparameters inside the Gaussian process emulation, we can use empirical-based method such as maximizing the marginal likelihood. And on the other hand, Gaussian process regression is a kernel method. The posterior mean estimation is actually equivalent to the result of a kernel ridge regression. This means we can also examine the results of Gaussian process regression from the perspective of reproducing kernel hyperspace in an analysis sense. A side note about this, actually, deep learning or neural networks also have connections with Gaussian processes. Under certain assumptions, Bayesian neural networks can be viewed as Gaussian processes with specifically defined kernels. And as I just mentioned, the Gaussian process regression has close connections to kernel ridge regression. And kernel ridge regression is actually function approximation inside reproducing kernel hyperspaces. A class of certain reproducing kernel hyperspaces will form a barren space, and the barren space is actually a proper function space where we can investigate the approximation properties of neural networks. So in this sense, we have a loop connecting the probabilistic viewpoints and analysis viewpoints of neural networks and Gaussian processes, right? And I believe out of this loop, there can be a lot of interesting results and observations to be explored and discovered. Okay, back to our model reduction game. We have applied our Gaussian process-based reduced order models, reduced order surrogate models in a variety of applications, including those in computational mechanics, like nonlinear structural analysis, nonlinear solid mechanics, as well as fluid dynamics and the fluid structure interaction. And more recently, we have been using our reduced order surrogate models in forward and inverse UQ, basically with our simulation-free online evaluations through the Gaussian process surrogates, we can generate however many samples we need in UQ estimates. If we can have a good control of our data-driven reduced order model, the bias in the uncertainty estimate would not be so large either. Okay, so this is our first part, using Gaussian processes for surrogate modeling in the reduced order sense. So this is a valid option for many applications because the surrogate modeling task is very easy to implement and it can work for many scenarios. But I have to admit that surrogate modeling has its limitations, especially has limitations in predictive performance, because the Gaussian process surrogates were only trying to approximate the reduced order solutions instead of trying to discover or trying to represent the dynamics underlying the data. And on the other hand, surrogate modeling can handle very well the interpolation of the of the solution manifold over the parametric variation. But if we want to predict for the future states, it will have a lot of limitations. From another viewpoint, in reality, we also do not always have full solution vectors as our data, right? We may have other forms of observations, such as images, photos, video, and so on, and other types of indirect data as our database. And how can we learn reduced order low dimensional dynamics out of this kind of data is also a question we need to think about. Combining these thoughts introduces my second method for today, it is reduce all the dynamical representation out of image data with deep kernel learning. And in this work, our research question was a little bit different. We tried to learn low-dimensional latent dynamics from high-dimensional measurements given by image data, and these images are often corrupted by significant noise. Since the noise is a lot of noise has been introduced, we especially need UQ here, right? So we are going to use probabilistic machine learning tools for the data-driven discovery and uncertainty quantification. And here you can see an example. We have a pendulum swinging back and forth, and we take photos of such a motion, and we can try to learn the dynamical representation in a low-dimensional manner out of this image data, and this image data are also corrupted by noise. The probabilistic machine learning tool we are going to use to address this is called deep kernel learning. In fact, deep kernel learning is a special type of manifold Gaussian process in the sense that the manifold embedded into the Gaussian process kernel is simply a neural network. And with such a setting, the Gaussian process can take high-dimensional data, for example, images as inputs. And in this sense, we can partially overcome the curse of dimensionality existing in Gaussian process emulation. And in this case, we also have our neural network parameters trained as Gaussian process hyperparameters. And I would also like to note that the training for such a deep kernel learning model is much simpler and cheaper than classical Bayesian neural networks. Okay, how should we use deep kernel learning to discover low-dimensional dynamical models? So still, we are going to follow the idea of the 3 R's, right? Remember, reduce, represent, and recover. And we have the high-dimensional noisy image data as our inputs, right? We put them into an autoencoder to reduce the dimensionality non-linearly, and then we have the low-dimensional latent space and the latent states. Right, and then we try to do representation, and in this work we are simply using a multi-layer neural network to approximate the map between the current reduced state and the current external action to the next reduced state. Basically, this neural network is trying to approximate a forward Euler scheme. Right? And after this, we use a decoder to recover back to the images. I would like to emphasize that we have the autoencoder and the multi-layer neural network for the dynamical model, both as deep kernel learning models. Basically, we are embedding a convolutional neural network here and a multi-layer neural network here into Gaussian processes to enable uncertainty quantification. In this case, both the uncertainties in the encoding and the uncertainties in the dynamical approximation would be covered by the deep kernel learning models. And we, together with all these 3 modules in this big model, we train them together and try to test how we can handle extracting dynamical systems out of high-dimensional image data. Okay, we did several tests. We added noise directly onto the image data, and we also try to add noise to the external control or external actions, or even we add noise to the underlying dynamics to make this system stochastic. And in all these cases, our model gave us very clear and compact representations of the low-dimensional dynamics. And also, I would like to emphasize that we have very clear denoising effect in the reconstruct images. Okay, so this is, I call this a gray box model because it is not black box, and we are having this deep kernel learning model in the representation step to approximate a forward Euler scheme. So it is trying to approximate certain dynamical structure underlying our images, right? So this is a gray box, but still we would like to think whether we can incorporate more physics into the training process to get more physically consistent reduction out of the data. So this will introduce our third method that we are going to discuss today. Is using Bayesian inference to estimate the reduced order operators. Okay, so we can start with an example. Suppose you are trying to solve Whiskas-Burger's equation. You can use your favorite spatial discretization for Whiskas-Burger's equation. For example, you can use finite difference over space, or finite volume, finite elements, whichever works for spatial discretization. And after this step, we will end up with a dynamical system in the full order sense, which is quadratic, right? Because the Whiskas-Burger's equation is a quadratic. We also know that if we have linear reduced spaces, once we have projected the full order system onto the linear reduced space, we will end up with a reduced order system being in the same formulation of a quadratic structure, only in a much reduced size. So the quadratic, the polynomial structure of the governing equation will still preserved, will only have a reduced dimensionality. If we recall how we do this in intrusive model reduction, actually we have to get the access to the code, to the full order code, to get the matrices A, H, B, and vector C, and then formulate the reduced order system through numerical projection and get the reduced order operators A hat, H hat, B hat, and C hat, right? And this is not something we want to do because that's intrusive. We may not have the access inside the full order code. That means we do not exactly know about the full order operators A, H, B, and C. But still, we know that the reduced order system through linear projection would follow a quadratic formulation. So we need a way to, an alternative way to figure out, to estimate our reduced order parameters, A hat, H hat, B hat, and C hat. Actually, the way we are resorting to is called data-driven reduced order operator inference. The idea is like following. So first of all, we gather our full order data for the full size vectors, full size snapshots Q. We gather the data of Q, and then we use POD to compress our reduced basis V. Then we project our Q data onto the V basis to get our reduced data for Q hat, right? And then we plug our Q hat data into our reduced order system formulation. And then we try to minimize the residual sum of squares for the reduced order system. By minimizing such a squared residual, we are going to have an estimate of the reduced order operators A hat, H hat, B hat, and C hat that best match our Q hat data, reduce the data in the minimum residual sense. Of course, and in the end of the day, at the end of the day, we will have a least squares problem. And of course, you can add your favorite regularization as necessary to improve as necessary to improve the estimate of our reduced order operators. Okay, so this is a data-driven learning process, and of course we may introduce a variety of uncertainties inside this throughout this process. For example, we may have noise in the data of the full order Q. And after the reduction, the noise will be reduced a little bit as well, but still there may exist noise in the reduced state data as well in Q hat. On the other hand, as you can see here, we need to approximate time derivatives to get time derivative data in this loss function. That means we have to perform, for example, finite differences to evaluate this, to approximate these time derivatives out of our state data. And this is going to introduce approximation error, which is another source of uncertainty in our data-driven learning process. Also, we use the regularization, and this is another source of uncertainty. And last but not least, we may have model misspecification. For example, if your underlying system for your data is actually a third order system with a minor third order term, but now we are assuming that the system is quadratic and ignoring the third order term, we have a model misspecification here, right? So these are many sources of the uncertainties that may be introduced into this operator inference framework. So this is why we want to do uncertainty quantification. We want to upgrade our deterministic or point estimate into a Bayesian inference so that we not only have a point estimate of our reduced order operators, but also a posterior distribution to describe the quantified uncertainties. Okay, so we started with a very simple setup. First of all, we define the residual of our reduced order system as a Gaussian type noise. In addition to that, we also define our prior on the reduced order operators as a joint Gaussian distribution with predefined mean vector and hyperparameterized variance. Then naturally we resort to the Bayes rule and have the posterior distribution for our reduced order operators with a new mean vector and a covariance matrix. So if we look closer at the posterior mean vector, we will see that this is actually equivalent to a deterministic least squares estimate with Tikhonov regularization, or the estimator through ridge regression. This is a common sense in Bayesian inversion, a well-known result. And in fact, in practice, we often need such a Tikhonov regularizer in our operator inference, because first of all, it may resolve the issues where you condition the Gram matrix D transpose D here. If this D transpose D is U conditioned, we do need such a regularizer to improve the condition number, because we have to invert this matrix, right? And in some other cases, we may also need the Tikhonov regularizer to help stabilize the reduced order time integration afterwards. But even though, even we have such a useful Tikhonov regularization, we are still introducing extra uncertainties into the operator inference process, right? We want to do the quantification of uncertainties for the use of Tikhonov regularizers. Actually, if we can recall, the Tikhonov regularizer is corresponding to the prior of our Bayesian inference. That means the definition of the penalty coefficient for the regularizer is equivalent to choosing good prior for our reduced order operators. So that means the quantifying the modeling uncertainties introduced by the Tikhonov regularization is naturally covered by such a Bayesian framework, right? And in this case, since we have a connection between the regularization choosing and the prior choosing, we can also use the perspective from both statistical learning and physics-based simulation to help us do the hyperparameter learning. So after we have the inference for our reduced order operators, we can sample over this posterior distribution of these parameters and have a lot of samples individually. And for each and every them, we can evaluate the reduced order dynamics, not only trying to reconstruct the history, but also predict for the future states. And we have an ensemble of such reduced order solutions, then we can have the statistics of such probabilistic reduced order solution. We have tested this method in several numerical examples. I'm going to show you one here. This is a 2D single injector combustion process, right? It's rather complex physics in 2D. We have fuel and oxidizer coming into the tube from the left-hand side, and the chemical reaction will take place inside the tube, right? And we were trying to use our Bayesian operator inference to have a low-dimensional dynamical representation of this system. As you can see from both the first 6 PUD modes and also for the x velocity at 4 critical locations. In terms of accuracy, we have the predictive mean quite close to the underlying reference. Not only for the reconstruction of the history data covered by the training, but also for the future states for quite a long time. And in terms of uncertainty quantification, we can see that both the errors in the mean prediction and the uncertainty band are increasing in a similar way. So this means that the confidence level is giving us a meaningful indication about how uncertainties are propagated from the estimates of the reduced order operators to the time integration over time. Okay. Maybe you have already realized when we did the Bayesian inference, we explicitly involved the time derivative data. And it is often the case that we do not have direct access to time derivatives. That means we often need to use numerical differentiation, for example, finite differences, to approximate time derivatives from the reduced state data. And this can work if the data are perfect, but what if we have noisy or scarce data, right? In those cases, the finite element approximations of the time derivatives would be very bad, and this will further compromise the quality of our operator inference. You may say that, okay, I know neural ODEs, right? In neural ODE treatment, we are directly incorporating time integrations into the loss function. We directly compare the integrated states to the state data. Basically, we are translating a differentiation into integration, and then we use either a joint state or automatic differentiation, depending on which type of time integration, either discrete or continuous you use. But this means extra efforts in the training stage. So more recently, together with some of our collaborators, we have been trying to figure out a simple way to address this issue. So basically, what we want to improve the predictiveness when data are noisy and or scarce. Basically, when finite difference cannot really approximate good time derivatives. And here we are thinking about a more generic setup for dynamical systems. Here I'm writing a dynamical system, right? And each and every line of the equation is parameterized on the left-hand side. So in this case, the learning of the dynamical system from the data is basically posed as a Bayesian inference problem to estimate theta I for each and every equation, in each and every equation in the dynamical system. Okay, so we want to figure out a way to conveniently do this Bayesian inference without using finite difference or other numerical approximations of the time derivatives. So this is our goal. And of course, if you consider this Fi on the right-hand side as a quadratic structure, and this theta I as our reduced order operators, and each xi is a reduced state in the reduced system. So basically, this system is going to be representing our reduced order system in the last couple of slides. But here we are considering a more generic setup. So here we are going to, again, use Gaussian process to help us. The assumption is that each and every state variable over time is a Gaussian process. And it's well known in the Gaussian process community that linear operations on Gaussian processes will not really change the Gaussian property. So linear operations on Gaussian process will remain Gaussian. So that means the joint distribution between the state, which is Gaussian process, and its time derivative will follow a vector valued Gaussian process. We just need to act the time derivatives at the proper locations in the kernels. Okay? And then we can use this to help us define a new likelihood. Okay, so let's recall what a likelihood is. So likelihood is the probability of certain evidence, like observations, data, measurements, or other types of measurements given the parameters we want to estimate, right? This is the likelihood function of our parameters. So let's consider what kind of evidence we can have in this scenario. So first of all, we have the time series data in the data-driven sense, right? This is for Gaussian process regression. We have the data, so we can do emulation. And actually, we have another sort of evidence in this setup. It is actually the formulation of our differential equations. So we can use the differential equation constraints given in this form as an additional evidence to be incorporated into our likelihood. As we just discussed, the joint distribution of the state and the time derivative will follow, again, a Gaussian process, and we can use this Gaussian process, this new joint Gaussian process, to define our joint likelihood. We just need to replace the right-hand side of the dynamical system. We just need to use the right-hand side of our dynamical system to replace the time derivative. And in this case, we are trying to match the left-hand side and the right-hand side of the dynamical system together. And in this sense, we are incorporating differential equations constraints into the definition of our likelihood. Okay, so this is how we define our likelihood in a new way. And of course, at the end of the day, we are going to have a Bayesian inference. Again, we have the prior as a joint normal distribution, and the newly likelihood as in the last slide. And then we have the posterior. Once we have the posterior distribution for the parameters theta I, we can have a Bayesian predictions by sampling over such a posterior theta I. Right. So actually, we can look more carefully at our posterior distributions for our parameters. I actually rearrange a little bit the formulation of our posterior distribution for theta I. As you can see here, the maximum posteriori MAP estimate of our theta I is actually equivalent to an estimator through generalized least squares regularized by a Tikhonov regularizer again. And it is in the generalized least squares formulation here, the target term d hat here is actually the mean estimate of our time derivatives through our Gaussian process emulation. And the weight matrix in our generalized least squares is actually the covariance matrix for the estimated time derivatives through GP. So in this sense, it means we are implicitly still trying to approximate time derivatives, but this approximation of the time derivatives is through the smoothing by a Gaussian process emulation. And more importantly, the uncertainties introduced by the smoothing process is automatically covered, automatically included in such a Bayesian inference framework. So in the end of the day, we have an estimate. We have an estimate that covered all the uncertainties involved in this learning process. That means if you have scarce or noisy data, but you have a very good Gaussian process, you can be relaxed, and the Gaussian process will help you denoise the data and give you a very good implicit estimation of the time derivatives. And using such a time derivative estimation, you can have a good estimate of your reduced order operators or the parameters in the dynamical system. We have tested this method in a few examples. This is still ongoing work, but I would like to share with you some of our preliminary results. So first example here is a Lotka-Volterra system. We are going to estimate the alpha, beta, delta, and gamma for parameters in this system using our newly defined likelihood through Gaussian processes. As you can see here, when we have no noise in the system, if we use either a lot of data or much reduced amount of data, the results are all very good, very decent. And then we try to make it more challenging. We increase the noise level to 10%. As you can see, if we use all the data we have, results are still good. 10% of the data are used. Quite nice, and 5% of the data, there could be some error, but the trend is still good. And then we try to make it even more challenging. We increase the level, noise level to 20%. With all of the data, still good results. 10% of the data, reasonable. 5% of the data, the error becomes larger and larger. But in the end, we can see that our method is quite robust with respect to noise level and sparse data, right? You can make it more and more challenging, and the method can still handle quite challenging cases. And how about we consider reduced order modeling? Here I'm showing you a very simple case. It's a heat equation, linear equation, right? And the reduced order model structure is linear, right? And we want to do the estimate of our reduced order parameters A hat, B hat, and C hat here, right? And as you can see, we can, when we have quite some noise in the full order states, once we use our newly defined Gaussian process-based likelihood, we can have a very decent estimate of the reduced order system. Once we recover back to the full order size, even at point-wise local points, we can still extract reasonable dynamical behavior out of the noisy data, right? Not only in the reconstruction of the history, but also for the predictions for the future states. And what if we reduce the number of data? Still, as you can see, the results are very good. So it seems like Gaussian processes are very good at denoising, and this can help us go around the derivative difficulty in the time series when the data are noise or scarce, and this can give us very good results in terms of predictions. So still, these are some very recent results, and I would like to hear some of your ideas, opinions, or suggestions. And I guess this is about what I want to share with you today. A few words as a summary, some take-home information. So today we have been discussing several different types of model reduction techniques in a probabilistic sense using probabilistic machine learning methods. The first one was about black box method using Gaussian process surrogate modeling. And the second one was the gray box using deep neural learning to represent low-dimensional dynamical systems out of noisy images. And the third method was Bayesian operator inference, basically using Bayesian inference to estimate reduced order operators with known physical structures. And in the end, we discussed how to use Gaussian processes to incorporate differential equation constraints into the likelihood definition so that we can improve the predictiveness, especially when the data are noisy or sparse. Okay, thank you very much, and I look forward to your comments, criticisms, suggestions, and discussions. Thank you.
Thank you so much for the wonderful talk, Memo. I enjoyed it a lot.
Thank you.
Let's have a Q&A session. All right, Kevin has a question in chat room. Yeah, I will. We will, give a chance a bit, yeah, after this.
Okay.
Kevin is asking in slides 15, 16.
15, 16. Okay, I'm
What
going
is
back.
yeah. He's asking, what is the loss function to train neural network and GP hyperparameters? That's
Thank you very
his
much.
question. Yeah.
Thank you very much. This is a very good question because the loss function was too long, so I didn't put it here. We trained these three models all together, so we have to combine the loss functions for these three parts all together. So I can tell you what they are, and of course you can refer to the paper to see more details. So first of all, we need to make sure that the encoding decoding is making sense, right? So we need MSE to match the reconstruction of the encoding decoding. This is one. Second one, we have to make sure this approximation of the fold Euler is making sense. So we have an MSE for this multi-layer perceptron as well. This is the second one. The third one will start to train the Gaussian processes, right? How to train Gaussian process hyperparameter, basically you can use maximum marginal likelihood or the minimum of negative log marginal likelihood, right? Then we have to incorporate the negative log marginal likelihood of all these Gaussian processes into the loss function. And in the end, we have to use variational inference to estimate the probability, right? So we also need to use elbow to replace the KL divergence. So all these terms will be combined together for the training of this big model. And you also feel free to refer to the paper for more details. But this was roughly the spirit. Yeah.
Okay, Sungwan has a second question. If you can go to slide 19.
Yeah.
This Bayesian inference is based on a prescribed reduced order model with uncertainty model parameters. Does your Bayesian inference quantify the model misspecification, for example, missing high order or exponential terms, etc.?
Thank you. This is definitely a very good question, and we have been thinking about this question as well. So of course, in our very first work, we simply used independent white noise, right? And it was not really covering the model misspecification. And of course, you can upgrade a little bit. You can use a Gaussian process to replace a white noise for this error term. So basically, that's basically trying to approximate your model misspecification or your closure as a Gaussian process surrogate. You can do that, but that's still limited. We are still trying to figure out better ways to do it, but based on such a framework, the best you can do is to try to use a Gaussian process to approximate this epsilon I as a surrogate model for the closure.
All right.
Yeah.
Thank you.
Okay.
I think next one was Abhijit. You raised your hand before. So if you can unmute yourself and ask a question, that would be awesome.
Yeah, please.
Can you hear me?
Yeah.
Yeah. Thank you so much for the amazing presentation. So you touched upon extracting the basis using POD, the Gaussian process, if I'm not wrong.
Yeah.
So say, for example, if a snapshot matrix has million by million data points, where you can't do D transpose D. I think you're doing D transpose D to reduce the dimension of the matrix to extract the preprocessing or POD modes from it. So I just need your opinion on this. Say, for example, you have a million by million data points in your snapshot matrix where you can't do D transpose D. What is a viable preprocessing tool to go for, like TEAM or PCA, if you're using some conventional ones, it's going to take a longer time to get those bases or interpolations point out of it. So what's your take on this when you have million by million data points or something like that?
Okay, thank you for your question. And let me repeat your question and see I'm understanding correctly. Okay, so you have a lot of data points. So that means this D matrix will be narrow but very long, right?
Yeah.
And if you do D transpose D, the computational cost is very large. And how to deal with how to deal with this? Okay, thank you.
Yeah.
We haven't met such a difficulty yet, but I have some ideas how to deal with this. So, for example, you don't need all of them to estimate your reduced order operators, right? You can take one snapshot among several, right? Every like 100 steps, you can take one. If that can still give you a good estimate, why not, right? Or you can use some other techniques. For example, you can use bootstrapping or ensemble to have. So each time you only have a subset of the samples and have an estimate, and you do this several times to form an ensemble and have a more probabilistic estimate of your reduced order operators. This is another strategy I can think of. And actually, in Cindy, they have already begun to use bootstrapping and ensemble to deal with this. And another strategy is actually our new method here, right? You can simply reduce the number of data and let Gaussian process to help you interpolate and extrapolate. Yeah, to interpolate in this case. Yeah.
Yeah, thank you so much for sharing. I'll look into those. Thanks.
Yeah,
Well, listening to that reply, I was simply curious, why can't you just use the HPC, like distributed those data and then do the D transpose D?
Yeah, that could also be an option. Yeah.
Okay. All right.
Yeah.
All right. Next question from John. Have you tried or compared against other system identification methods like OKID, MOESPI? I don't even know how to pronounce it. MOS?
I can tell, sorry, I used an acronym, UNSU. So observer, Kalman filter, identification, and multivariate output error state space.
Well, are you aware of that, Mengo?
I'm sorry, maybe I have limited knowledge to address this, but a comment I can provide is that basically our method here, for example, for this Gaussian process likelihood definition method, this can be embedded into a lot of methods, right? This is just a new way to define a likelihood. If you are wherever you need likelihood, you may think whether this likelihood can be used in your favorite method, right? For example, we can use this likelihood in operator inference like I did before, or you can use a similarly defined likelihood in Cindy, right? It's also an option. So I would say that our Gaussian process-based likelihood definition is more like a plugin, right? You can use this to you can plug this into your inference framework if it is okay to use. Yeah, this is the comment I can provide. And of course, feel free to write me an email about your specific considerations, and I'm happy to discuss.
Okay.
Yeah. For example, will you go at Mortec next week? I'll be there.
Yeah,
Where?
let's see. Where?
Mortec 2023 in Paris.
I'm sorry, I'm not going, I guess.
Okay.
Yeah.
No worries.
Paris, yeah.
I shoot you an email.
Yeah, we wrote email before, right? So I know your email. Let's communicate based on that.
That's right. We did emails in the past. Thank you so much.
Yeah.
Great presentation.
Yeah. Thank you.
Awesome. Can I ask a question?
Sure. Go ahead.
All right. So one time in your presentation, you mentioned that deep kernel learning training cost is less than Bayesian neural network.
Yeah.
But I can see that because the Bayesian neural network is really, really expensive to train. But I see that deep kernel learning still has the component of neural network, and it is combined with the GP later on. So the training of the DKL, the deep kernel learning, it should be as expensive as just training the normal neural network.
Yeah,
isn't it?
Yeah, I think so. It's indeed. For example, we use a maximum marginal likelihood to train this manifold GP. So basically, that's comparable to the training of a deterministic neural network, but with a different loss function. So this is cheaper than the training of a Bayesian neural network, right?
I see.
So
Okay.
the computational cost is saved in this sense.
I see. Yeah, but the deterministic neural network training of that is not an easy task as you increase the data size, because you have to solve the nonlinear optimization problem.
That's true.
So you still have an issue of scaling in that sense.
I would admit yes.
Yeah.
Because of the neural network existing in this model. Yeah.
Right. But I mean, other compression technique. I mean, a lot of times, you presented 3 or 4 different methods. I think 2 or 3 was, based on the POD, like the linear compression.
Because we like it.
we like it because the training of that is, very a lot less complex than training the neural network, but it has a disadvantage, like it cannot accurately represent the advection dynamics, for example, or the Kolmogorov is decaying slow. Yes, but in that sense, deep kernel learning would be beneficial because you are using the neural network to compress. Any comments on that?
I have a very mixed feeling. Some of my work, I do use the autoencoder or similar tools for nonlinear manifold learning because they are useful and popular, of course. But for example, if you use the convolutional autoencoder here, you don't have as good error control as in POD, right? Many things are unknown. And if you want to do a more physically meaningful projection onto the nonlinear latent space, of course you can do least squares Petrov-Galerkin. That's one way. So I guess Yongsu knows that very well. Yeah, that's one way, but it's not always convenient either. Especially when your neural network encoder is very, very complex. The projection could be very tricky. And if we do black box learning or black box or gray box learning, we are missing some physics. So I have a mixed feeling about it. So if we have linear PCA, we can do the linear projection in a very decent way. Of course, it's not the best way. But basically, we have to compromise either here or that. Maybe someone in the audience come at us with a very good idea. Maybe that can be revolutionary. Revolutionary. Yeah. I don't have a clear answer for that yet.
I don't think anyone has a clear answer for that. Yeah. So I think I ask you a difficult question. I love the your method of dealing with the noisy data. Basically using the Gaussian process to smooth those data and then get the robust accuracy. I saw in experiments you tried up to 10% noise level.
Yeah.
Have you tried to increase that noise level, like maybe 100% noise level?
Yeah, I showed
20%.
20%.
Okay.
We also tried a little bit more, 30%, but that's not gonna work very well. So this is how we roughly define the level of noise. Basically, so we enrich the solution data to get a rough order of magnitude of the solution data, and so 10% means that 10% of that would be the standard deviation for the white noise we add onto the data. So in that sense, if we increase to 100%, the data not really making sense at all. right? Yeah. So in this sense, 20-30% would already be quite large. And in reality, even though we have data in the real world sensing system, but it wouldn't be so large, right? You introduce some error, but the level is up to some limit.
Okay, so 20%, you think it's a reasonable noise
I
level?
think 20-30% would be a reasonable
I see.
setup. Yeah.
Okay, sounds good. We actually have a recent work. It's about to be published. We are introducing another way of dealing with those noise data as well.
Yeah.
You're using Gaussian process, but we are using the weak Cindy, like the
weak
integral.
Cindy,
Yeah, integral form of the sparse identification of nonlinear dynamics.
Basically, you have your PDEs and you have a weight, you have a test functions and do partial integration by part, so that the noise will come from this counterpart to the other one. Right?
Yeah, exactly. But we use the weak Cindy in the latent space. So we do the compression first, like either POD or autoencoder, and then apply the weak Cindy in the latent space, reduced space. There, when we apply the noise level like up to 50%, even like higher, we got remarkable accuracy, very surprising accuracy. So I will definitely share those work with you.
Thank you. That would be very helpful. But I do actually have a question for that. So if you use a weak Cindy, it's very critical how to choose the test functions, right?
Right. We use the piecewise, the compactly supported the basis functions, and it is sensitive to how we change the radius, like the width of that compactness. So you have to tune for that depending on the applications.
Yeah. That's my impression too. It's very good to have this confirmed. Thank you.
Yeah. Maybe last question from me. So you show the 2D single injector combustion process.
Yeah.
If you can go to that slide, I don't know the slide number.
Yeah, this one.
Yeah, what is Y here? Y1, Y2, Y3, Y4.
Y? Which?
So in the definition of Q of C vector.
It's the fractions of the.
So it's a two-phase flow.
Yeah.
Awesome.
Yeah, it's the fractions of the components. Yeah.
Like the volume fractions.
Yeah.
That's great. And you apply the you use the POD most.
Yeah, we did the POD. Yes.
Yeah, this is
It's complicated. Yes, this is indeed the case where POD may not be the best choice, but we use a lot of POD modes in the end to guarantee the approximation is still decent.
And I mean, you're doing extrapolation too, like in time.
Yeah, we're doing extrapolation too. We used 60-ish POD modes, if I remember correctly. I have to refer to the paper to refresh my memory, but we indeed use a lot of POD modes.
Oh, okay. Yeah. Awesome. I loved it. So I think we need to talk about this.
Yeah.
All right. Any other questions from audience? If not, let's thank our speaker, Meng-Wu, for the wonderful talk and, all the nice research he presented. Thank you so much.
Thank you. Thank you for the invitation and all the nice discussions and communications. Thank you.
Awesome. Okay, let me push the stop button.